When conducting a hypothesis test, it's really our goal to be able to convert the information within our sample to allow us to draw conclusions about the population. And in order to do this, we need to be able to connect the statistics, the test statistics, the null distribution or the sampling distribution over to statements about the hypotheses themselves or about the population at large. And in order to do that, we really make use of the probability information that is contained within the null distribution. So if we want to draw conclusions based on a hypothesis test, then it's possible for us to compare observations in order or against set standards of evidence that are derived from the null distribution. So what we can do is we can actually observe what is in our sample, and then we can compare that to values that are coming out of the null distribution and ask, well, did we observe something that sort of contradicts the null distribution based on the values we're sort of seeing, or is what we're observing sort of concordant with that null distribution? Okay, so we can think about how does evidence and hypothesis testing go hand in hand, right? And so when we're running a hypothesis test, the test statistic is computed, and that's used to determine whether the data are contradicting the stated null hypothesis or not. Okay? Our test statistics have known null distributions, right? So every statistic has a sampling distribution, but a test statistic is special because the test statistic has a null distribution. The null distribution is the distribution of the test statistic under the null hypothesis. And so if the null hypothesis holds, the distribution of the test statistic is completely known. There is nothing within that distribution that we do not know anymore. And what that means is we can use the null distribution in order to calculate probabilities or make probabilistic statements regarding the population or regarding the hypotheses themselves. So for instance, we might ask, how much evidence would we have required in order for us to disbelieve the null hypothesis? The null hypothesis is what we're believing by default. And so we can ask ourselves, and this is going to depend on the context, it's going to depend on the situation, it's going to depend on, sort of how much is riding on us getting these decisions right. But how much evidence do we actually require in order for us to not believe that the null hypothesis is true? In other words, how extreme of an observation do we need to make in order for us to doubt that the null hypothesis is actually accurate? So we might, for instance, set up a hypothesis test of testing that the mean is equal to some value mu naught, right? And we can do this versus a two-sided alternative. And if we are using sort of the sample mean, then really what we're asking with this question is how large or how small would the sample mean have had to have been for us to doubt that it is actually equal to mu naught, right? And so in other words, we could say, well, any observation that is more than d units away from mu naught, so if x bar was less than mu naught minus d, or if it was mu naught plus d or bigger, then that's strong enough evidence. And for us, really the question then becomes, well, how do we decide on what d is here? So if we think about the example of flipping a coin and trying to determine, is this a fair coin or not, right? The question is, well, we know that if you were to flip this coin 100 times, you're expecting to see 50 heads come up. But how many heads would you have to see in order for you to doubt that this is a fair coin, right? Maybe you say, well, I would want to see at least 70 heads or fewer than 30 heads, right? Perhaps that's sort of your level of standard there. And in that case, you'd be taking d is equal to 20, right? And then you'd be saying, if I've observed the expected number, which is 50, minus 20, so 30 or fewer, or if you observe the expected number plus 20, so 70 or more, then you would doubt that this is actually true, right? But if you don't observe something that extreme, then you have no reason to doubt the null hypothesis. Okay. Alternatively, if we had thought about a one-tailed test here, right? So we have the null hypothesis is that the proportion is less than or equal to some standard versus the alternative is that the proportion is greater than that standard, then we could say, well, we would need to observe something that is sufficiently large, right? So we would have to observe our sample proportion to be p naught plus d as strong enough evidence, right? And so again, our question really is going to become, how do we pick that value of d, right? Where is the d going to be coming from? But we're just sort of looking for this to be sort of set up as strong enough evidence to contradict the null hypothesis that we're dealing with. In order to run a hypothesis test in this manner, we can ask sort of the amount of evidence that we need to observe in order to contradict our null hypothesis. And then what we can do is we can compare the values that we actually observe to those standards, right? So we can actually go out and we can say, well, did we observe something that goes beyond that standard? And if we did, then we are sort of contradicting our null hypothesis, and we can reject the null hypothesis at that point. If we didn't observe sort of enough evidence to contradict that, then we have no reason to doubt the null hypothesis, and we can act as though the null hypothesis is actually true. So ultimately, when we're trying to come up with how much evidence do we need, what we're really circling on here is this idea of critical values. So in order to figure out how much evidence is sufficient, we need to turn to these critical values. The critical values are defined on the basis of the cumulative distribution function of the sampling or the null distribution, right? So we take ft to be the cumulative distribution function of t. Right? And in particular, we're thinking about t as our test statistic, and so ft is the cumulative distribution function under the null hypothesis, right? Then the alpha level critical value is going to be f of t is equal to alpha, right? So f of t alpha is equal to alpha. So we solve this expression right here. We find what is the value t alpha. So what is the value? And we call that t sub alpha, such that the probability that t is less than or equal to t alpha equals alpha, right? And whatever this value for t alpha is, we call that the alpha level critical value, right? And so it's a value that's coming from the cumulative distribution function, and it's a value that we could find in theory for any distribution, though typically we're going to be using sort of computers to work them out, right? And so interpreting this, the probability of observing t less than t alpha is exactly equal to alpha. That's how the critical value is going to be defined. Now, in order to draw conclusions in our hypothesis test, what we're going to be doing is comparing observed values to critical values in order to determine whether or not we need to reject the null hypothesis. And so the critical value is going to be calibrated based on the level of significance, or how much evidence we're actually looking for in our sample, in order to decide whether we need to reject the null hypothesis or not. When we're dealing with the hypothesis testing, the critical values are ultimately coming from the null distribution. So if we're thinking about what is the cumulative distribution function that we're actually taking a look at, where's this ft? Well, this ft is going to be coming from the null distribution, right? So we need to know what our null distribution is in order to find a critical value. And then the general point is that if our observed test statistic is more extreme than the critical value, and so when we're saying more extreme, we mean sort of larger than the positive version or smaller than the negative version, depending on what hypothesis test we're actually looking at, then that's going to serve as evidence against the null, because we've observed something that is actually outside of those critical values that we're looking at, right? And so this occurs directly if we have a symmetric null distribution, right? You need to be thinking about it being at least that far away if it's non-symmetric, but most of the time when you're dealing with hypothesis testing, the null distribution is going to be symmetric. And so you can think about it as, did you observe something that was larger than the critical value or not? So formally, if we want alpha to be our level of significance, then t alpha are going to be the critical values from t, right? So if you take t sub alpha, that is the critical value of t. Then depending on the hypothesis, we can figure out what critical values are the relevant critical values for us. And so if we have a two-sided hypothesis test, then we're going to have two critical values. We're going to have one on the lower end, and if you observe something smaller than the lower one, then that's evidence against the null. Or if you observe something larger than the higher one, right? So if you're outside of the range of critical values. And in particular, we're going to take those to be t alpha over 2, right? So alpha over 2 as the smaller side, and then t of 1 minus alpha over 2 as the upper side, right? So we have those two sort of tail critical values there. If you are looking at the null hypothesis is that the parameter is less than or equal to some threshold, then the only thing that you care about is the upper tail, right? Because you're just saying, well, what is actually going to be contradicting the null hypothesis here? And in our case, if the null hypothesis is that things are small, the only thing that contradicts it is that things are large. So you're just looking at the upper tail, and in particular, it's going to be t of 1 minus alpha. Okay, and so notice that the upper tail here, t1 minus alpha, is different from this t1 minus alpha over 2. And the reason is that when we're dealing with a single tail, we get to put all of this alpha probability on just one side, whereas in this case of the two-tail test, we have to take alpha over 2 above, and we take alpha over 2 below. And so we're thinking about sort of distributing our level of significance to above and below the above and below in the two-tail case and just above in the one-tail case. Similarly, if we take the upper tail null, right, so theta is greater than or equal to theta naught, then the relevant critical value is going to be t sub alpha, right? And so again, we have just the lower value. Anything that you observe that's smaller than this is going to be evidence against the null hypothesis. And once again, we have t alpha rather than t alpha over 2. Okay, so our critical values will change depending on whether we're looking at a one-tail or a two-tail test. Now we can look at an example of this to work out, well, what are the critical values that are of interest to us? And so here we're dealing with a sample x1 through xn, and this sample is going to be coming from a normal distribution where the mean is unknown, so we're just calling that mu, and the variance is equal to 1. And so we have our unknown mean, that's what we're interested in, right? We want to test mu is equal to 4 versus mu is not equal to 4. We're taking a sample of size 10, and we find that the sample mean is 3.4. And what we're asking for is, what is the critical values, or what are the critical values, if we need more than one of them, for this hypothesis test at alpha is equal to 0.05. And so the first thing to note is that we are dealing with a two-tail hypothesis test here, right? We have the two-sided alternative, and so we know that we're going to need two critical values here, right? So we need two critical values. And these critical values, what we really want to be doing is we want to take alpha over 2 and put it as the lower tail, and we want to take alpha over 2 and put it at the upper tail, right? And so we have to think about, well, how are we going to be getting these critical values? And for that, we need sort of our test statistic. We always want to be thinking sort of through what the relevant test statistic is going to be. And so in our case, we could take x bar to be our relevant test statistic, right? And so then what we're really thinking is, okay, well, we're testing this null hypothesis of mu equals 4, and then versus, say, the alternative of mu is not equal to 4. Okay, and so what we want is we want to say, well, how far below or how far above do we need to be? We know that x bar is going to be a normally distributed random variable under the null hypothesis, right? So under the null hypothesis, this is going to be a normal with a 4 and then a 1 over 10 as the variance, right? And so in this case, we can sort of think about this normal distribution and ask ourselves, well, how do we figure out where the critical values are here? And what we're thinking about, right, if we put out our normal distribution, it's going to be centered on a 4. Right, we can draw in our sort of rough sketched bell curve here. What we want to say is we need to find the values, and we'll put some value down here, and we'll call this t alpha over 2, and then we'll put some value up here, and we'll call this t1 minus alpha over 2. Okay, and what we want to find is the value such that there is alpha over 2 probability over here, and there's alpha over 2 probability up here. Okay, and so from our critical values, what we are going to need is we need the t alpha over 2, and in this case, alpha is equal to 0.05, right? So we're looking for the t 0.025 and then the t 0.975, where we're coming, these values are coming from the normal for 110. And what we're saying there is then if you observe something that is outside of this range, right? So we have this sort of window from between these two critical values. If you're outside of that window, then that's evidence against the true value being 4, right? Because it would be unlikely to see that if that's not the case. And so that's sort of the process we're thinking about here, okay? And so we can walk through this and say, if we wanted to test using the sample mean, then we know that the sample mean follows the 4, 1, 10 distribution. Because it's a two-sided test, we need alpha over 2 and 1 minus alpha over 2. And so then we need these specific critical values, right? And so we need t of 0.05 over 2, which is t of 0.025. And so specifically, that's going to be f of t of 0.025 equals 0.025, right? That's what that is actually defined as. And similarly, we're going to need the upper tail version as well. So that's t of 0.975, where that's defined to be f of t 0.975 is equal to 0.975, okay? And f here is the normal for 110 cumulative distribution function. And so we can sort of write that as the values that we actually need. If we want to find them, the easiest way to find them is to turn to a computer. And so in particular, in R, if you want to find the critical values from the normal, we can use the qnorm function, right? And so the qnorm function takes in the level that we want here. So this 0.025 corresponds to our 0.025. And then we need to specify what is the mean and the variance, or the mean and the standard deviation that we're working with. So here the mean is 4, and the standard deviation, which we call SD, is the square root of 1 over 10. Right? And so the square root of 1 over 10. If you don't provide the mean and the standard deviation here, then it's going to assume that you're dealing with a standard normal, right? And that's not what we want here. We want from this normal distribution over here. Okay. Similarly, if you want the upper tail value here, we can take Q norm is going to be 0.975, right? Where that's coming from this level here. The mean is 4, and this standard deviation is the square root of 1 over 10. Okay. These values, if you actually work out what they are using R, that gives you about 3.4 and then about 4.6, right? And so we're looking at 3.4 to 4.6 as the critical values. And so in our case, if you actually look, our 3.4 is actually within these two values here, right? 3.4 is larger than 3.38. And so there's not actually evidence against this null hypothesis in this sample here, right? So 3.4 is larger than the smaller value. We're not sitting outside of that region, we're sitting within the region. And so there's insufficient evidence to reject the null hypothesis based on this example. Okay. You can take a look at sort of the similar example, but with a changed null hypothesis here, right? And so everything is the same, except now we're testing mu is less than or equal to 4 versus the alternative that mu is greater than 4. And so we have the exact same sample, we have the exact same distribution. And so here, instead of us looking for those two different critical values, we're going to be focused on a single critical value. And that critical value is going to be the critical value that sits at the upper end, right? Because we need sort of the critical level to be a sufficiently large value. We're still working with alpha equals 0.05. And so again, we have our null distribution is the normal for 110, but because this is an upper tailed alternative, we need one critical value, and that critical value has to occur at 1 minus alpha, or 0.95 in this case, right? So we need the critical value t of 1 minus 0.05, which is t of 0.95. And again, the definition of this critical value is f of t 0.95 equals 0.95, where f is our cumulative distribution function for the normal distribution that we're dealing with. So again, once we know this is the critical value we're looking for, we can turn to the computer to find it, and we're going to use this q norm function again, right? So it's q norm, now our level is 0.95, so we plug in 0.95, and there's a typo in this, right? There shouldn't be that extra 0 there, but that's okay, right? We should have the decimal point is right there. But we type in 0.95 to match the level. We have the mean of 4 coming from the mean here. Standard deviation is the square root of 1 over 10, which is coming from the distribution there. And if you actually work out what this critical value is, that gives you 4.5201. And so this critical value is a little bit larger than the upper tail in the previous case, right? And so that's coming because we're actually changing the level, or sorry, it's a little bit smaller than the value we were looking at in the last example there. But in our case, we still don't observe something that is larger than it, right? 3.4 is still smaller than this value, and so there's no evidence against the null hypothesis. And once again, this should make some sense to us because we're observing a sample mean of 3.4, right? And the sample mean is exactly part of the null hypothesis here. So we shouldn't observe much evidence against it, and using these critical values, we don't observe much evidence against it because 3.4 is smaller than 4.5, okay? And so we can look at sort of the last example here where we're looking at the other null hypothesis. So now we're saying the null is that it's greater than, the alternative is that it's less than, right? And so same sample size, everything's the same. So in order to find these critical values, because this is a one tail alternative, we're going to need exactly one critical value, right? That critical value has to occur at alpha because it's the lower tail critical value, right? We need something to be smaller than 4 in order for it to be in favor of the alternative. And so that's what we're looking for, right? So we have the same null distribution, a 4, 110 normal. It's a lower tail alternative, and so we need one critical value. That critical value is going to occur at the alpha level. And so specifically, we're looking for t of 0.05, where t of 0.05 is defined such that f of t of 0.05 equals 0.05. And again, f is the cumulative distribution function for the normal distribution that we're dealing with. Again, once we're here, we can turn towards software to determine this for us, right? And so here we're looking for Q norm of 0.05, right? 0.05 is matching the level here. The mean is 4. The standard deviation is the square root of 1 over 10. And when we actually fill this out, we find that that critical value is 3.4799. Now notice in this case, for the first time in sort of these three examples, we find that 3.4 is actually smaller than the 3.4799. And so what that's saying is that we've actually observed something that is more extreme than the critical value that we're dealing with, right? So if we sort of sketch out what this looks like in terms of our normal curve right here, right? So we have their mean is occurring at this 4, okay? And then what we've done is we've come in and we've said, well, this value right here is going to be at 3.4799, okay? And so this value is chosen such that there is 5% probability of being lower than it, right? So this is 0.05 down here. And anything that we observe that's in this tail, that's providing sufficient evidence against the null hypothesis. And in particular, we only have one tail because the null hypothesis is it's 4 or greater, right? And so anything that falls sort of sufficiently far this way is going to be evidence against. And we're observing we're observing it at 3.4, which actually falls, into this red mark here. And so because of that, we've observed evidence against the null hypothesis, right? So we observe something that is more extreme than the critical value. And so since 3.4 is less than our critical value, there is sufficient evidence against the null hypothesis, okay? So if we can compute those critical values, if we can use the software to determine the specific values of them after we figure out which ones do we need, then how do we go about actually using them? So once you actually have computed a critical value, then that's going to serve as the point of comparison for the observed test statistic, right? So if the value is more extreme, if it sits outside of those critical values, then you reject the null hypothesis. And if you're rejecting the null hypothesis, we accept the alternative as sort of this more plausible explanation of the observed data, right? Based on the data we've observed, then because we observed something that was extreme enough, then the null hypothesis doesn't seem particularly likely, okay? If you don't, so if you observe something that is within the bounds of your critical values, then you fail to reject the null hypothesis. We can never accept the null hypothesis. However, if you fail to reject the null, then you're sort of acting as though the null hypothesis is actually true. And that's because we're starting from the assumption that the null hypothesis is true. And so it's the thing that we don't need evidence to believe. Okay. Now, intuitively, what we're thinking about is that if the null hypothesis is true, it's going to be very unlikely for us to observe something more extreme than the critical value. The probability that we observe something more extreme than the critical value, if the null hypothesis is actually true, is going to be alpha, right? So we've set up the critical values in such a way that there's alpha probability of observing something outside of the null hypothesis or outside of the critical value range, assuming that the null hypothesis is true. And so because of that, if we observe something that is sort of more extreme, then that's saying the null hypothesis does not look particularly true. So just to emphasize sort of what's going on there with that, right? If we are thinking about the null distribution, right? So we can come in and we can sketch out that this is the distribution assuming that the null hypothesis is true, right? So this is the null distribution. Okay. The way that we've set up our critical values, and we'll look at a two-tail test here just because I think that that's sort of the most informative, but the same process is going to happen with a one-tail test, right? The two-tail test is going to set up one critical value here, which we've been calling T alpha over 2, and we have one tail here, which we've been calling T of 1 minus alpha over 2. And these critical values are computed such that there is an alpha over 2 probability of this happening, right? So there's alpha over 2 probability down here, and there's alpha over 2 probability up above here as well, right? And the reason for that is we know that there's 1 minus alpha over 2 probability below it, right? So there's 1 minus alpha over 2, all of this. And so if you're sort of taking the complement probability, that means there's there's alpha over 2 above it, right? So that's sort of where we're getting that from. But so what we're saying here with this is that the probability that we observe anything in the highlighted region here is alpha over 2 plus alpha over 2, right? So we have alpha over 2 plus alpha over 2, which is equal to alpha. According to this distribution, there is an alpha probability that we observe anything sort of in the extremes of this distribution, okay? Now, this distribution is the distribution that occurs if the null hypothesis is true, right? So if the null hypothesis is true, then there's an alpha probability of observing anything outside of, observing outside our interval from t alpha over 2 to t1 minus alpha over 2. Right? That's the probability that we observe something out there. And so then if we go along and we actually compute our test statistic and it comes up here, right? There's a very rare chance that that's going to happen if the null hypothesis is true, right? So this right here, this is rare if H naught. Okay? And so because of that, it's going to be sort of the data are suggesting that we can reject the null hypothesis, right? If, on the other hand, we observe something in here, then that's not rare if the null hypothesis is true. And so that's where our critical values are coming from, right? It's sort of useful to have that picture, to keep that picture in mind. But that's where we're saying if you observe something that is outside of that range, then you can reject the null hypothesis. And so if we're observing something more extreme, then we reject the null hypothesis because the null hypothesis is unlikely in that case. And so if you think it's unlikely that the null holds, we reject it. We accept the alternative as a better explanation for what's generating the data. Okay. So in order for us to draw conclusions from hypothesis tests, one of the ways that we can do that is to use the null distribution to determine our critical values, and those are going to serve as the standards of evidence. And we're just going to take those and we're going to say, is what we observed larger than those critical values? And if it is, then we can reject the null hypothesis. If it's not larger than those critical values, then we're going to fail to reject the null hypothesis, right? And so these critical values that arise out of the null distribution are going to serve as those standards of evidence, and using those, we can then compare what we actually observed in order to draw conclusions about the hypotheses that we actually care about.